impressed. Okay? Me, I did. But I don't know whether you did. Because I will know whether you did or not. I gave you some things to do at home. Did we do them? No, so you didn't sleep well. All right. Okay, this morning we'll start MAG, magnetoacoustic gravity waves. We have considered the problem of MHD waves under the ideal MHD, where the dissipative times were ignored. We're also going to ignore them here. But rather, we'll add an additional term, gravity. And the gravity will help us, particularly in modeling photosphere and chromosphere as the solar atmosphere. So we'll just begin. Go back to our equations. You will see equation 5.1 still stands. And I know by now you'll be able to write the equation of continuity. We can write that, is it not? Okay. Now when we come to momentum equation, please, it's only one row. It's only one row, not the two of them. It's the guy who was copying it for me. Okay. Now, it's not like that in your notes. Okay? We had the first term and the last term previously. We only added the effect of gravity. And you should also notice something in my lecture notes. Normally, we could say a vector A. We put this, is it not? In the note, I'm using a bold face. So bold face, they are the same, eh? Okay? Uh-huh. So don't take those ones that are bold as scalars. They are not scalars. All right. Now, the energy equation or the Bertic is still the same. You can see we have expanded that. You see where we had d by the t of this over this is actually dp by the t minus, I think, rho by the t. So that when you expand them, you'll be able to pick out something that will come. There should be a gamma dash. So that by the time you now do the necessary things, here becomes the sound wave. Okay. Now, having looked at that equation, the same here, induction is the same, where this is this. Now, the next thing we will do, okay, we will see a connection with the thermodynamics, where we are trying to look at the temperature within the environment to be equal to m, the mean mass particle, over the Boltzmann constant, rho multiplied by the pressure. That is what happens in ideal gas law. I think we all did the thermodynamics. Okay, fine. Now, the value, you can see the value of Kb is small. So most times, some people might try to non-dimensionalize, to remove these from calculations, except you have a very good computer. All right. Now, as usual, we'll go over to our equilibrium. What happens with equilibrium? All the partial derivative with respect to time, partial by partial t, will tend to zero at equilibrium. And at equilibrium, the V, which is equal to V naught, is equal to what? 0. That is what happens with equilibrium. If you go back to this equation, this is 0. This will be 0. So equation 5.1 will not contribute to equilibrium. You come over to the energy equation. The first term will vanish. This one does not contribute. So the only one that will contribute is equation 5.2. And the left-hand side will vanish. And then you'll be left with the grad of P will give us minus rho G plus J cross B. 0, 0. Let's just put that. Because we are taking this to be our zeros, to be our equilibrium position. So that's exactly what we will get. And the next thing that comes in there is that your J 0 cross B0 will also be equal to 0. What is our J? J0 will be 1 over mu 0 of what? Curl of B0. All right? That's exactly what we will get. Now, somebody was asking me yesterday, why didn't we take the curl of B0 called B1? B0 is a constant. The curl of it will vanish. I think you were the one. That's why we didn't have that second curl. All right. Now, having done this, you will see that equation 5.9 will imply that the Lorentz force is not allowed in approximation because the pressure gradient of gravity would be so strong enough. Mayoga, you see, when the pressure term of gravity is so great, you are approaching the area of what? The black hole under your gravitation. So that is why most times the current density, electrical current density, is not permissible in the black hole. And that is why this equation is telling you this. All right. Now you see, what will now be left? There is something that will happen here. In the corona, for example, the beta plasma beta is usually less than 1, less than 1, far greater than 1. And that happens, we now have what we call a force-free medium. What does that force-free medium stands for? The curl of B will vanish. All right? Curl B will vanish. And then if curl B vanishes, what happens in equation 5.8 will simply give you that the grad of P0 will give you minus G rho 0. That is what we will get. And we are taking the direction of flow to be in the direction of Z. This will now change to partial by partial Z. You see how that equation is obtained. You see how we obtain this. And then if you use the fact that our sound speed, we have defined it before, is that, what are we going to get? You will see that when you make the substitution, just that one is algebra, so I'm not going to write. So you'll be able to have that row Z will give you this. And then you can integrate this. This is either you call it variable separable. I think you know how to do variable separable. You know, if you don't know, tell us. Or you can also look at it as a linear equation such that the solution gives you this. Okay? Are we through with it? If you don't know, let's see. Because you are here to learn. Let's say you have the P naught by the Z is equal to, I call the whole of that one constant. So I call this minus P0. You can separate the variables. You have the P0 by what? P0 will be equal to what? Minus the Z. Is it not? You integrate this. What are you going to have? You have natural logarithm of P0 will be equal to minus what? Z, plus of course a constant. I take exponential of both sides. E ln P0 will be equal to another constant, E minus a Z, which if I drop, I will have that P0 will be equal to A E minus Z. That's exactly how we do that integration. It's quite simple. Are you following me? So that's how we obtained this solution. But you look at it, it looks a little bit messy. We want to clean it up. We now define scale height, H, to be equal to P0 over rho over G rho naught. And then we put the value of P0 from our previous definition that has to do with the temperature. Or you see, it tells you you are here. So you look at your P, T naught this, that will reduce it so that you will be able to utilize this. And that gives us that you have H will be equal to CS squared over rho G. We look at here, we have C S squared over rho G, which is an inverse of minus what? Of H. So that is how we define the scale height. And that gives us this. To be your initial pressure, of which for the value of P at 0 will give you this. You'll be able to plot it. Maybe at the end of the day we can plot that with Mathematica. Now, what happens with rho? Because rho is related to P. We'll go back here. You will see here, P previously, what did we get P? If you come down here, you will see they are related. Of course, we are going to have that. Rho from equation number 511 says rho naught will be equal to gamma P naught over CS squared. So all we'll do, rho naught will be equal to rho P naught squared over CS squared, multiplied by P naught. And what would that give us? The equation number 517. So that tells us, interpretation tells us that the pressure at equilibrium is a decaying function. Okay? It decays with height. So as you are moving up, it reduces. That's just interpretation, both the two of them, pressure and density. I hope here is okay. So we'll be able to talk about the equilibrium under force free. And that is what is attainable at that height in astrophysical environment. Now, I just give you some remarks. You notice that because of the presence of gravity, the medium now is what? Stratified. There's an inhomogeneity. Unlike before, we have that the pressure remains constant. But in this case, pressure is not constant. And your initial pressure density is no longer zero. Rather, it is an exponential decay function. That is because of introduction of what? Of gravity. Now, the presence of length scale. I think there's something missing here. Okay. Introduced by gravity, introduced what they call a time scale. And this area is very, very important when we start talking about the frequency as we go on, which you will know by the time you go into research on this area. Now, in terms of this, and taking into consideration the acoustic speed, you will see that this time is the time it takes the sound wave to propagate over a distance h and comes back. So it means it will go, cover h, it will come back again, another h. That is why you're having 2h. So that time scale tells 2h over cs is this. And then we will call that value where we have the order of omega a equal to cs over 2h is known as the cutoff frequency. My brother, I think you are the one looking for cutoff frequency. So that is how, and that cutoff frequency comes in as a result of the effect of gravity. So it modifies everything. So I give you one question. You will help us search through your Google. They've given you data. What is the significance of cutoff frequency in wave propagation in the solar atmosphere? The significance of cutoff frequency. You see, today is easier because we are building on what we have before, is it not? Okay. Now, this is where we'll start. You want something back? Okay? Okay. That's what? Boundaries. So you have a bandwidth. Uh-huh. You see like what we are doing. Prof, you see, under this cutoff frequency, that those of them who are interested or those who research in radio astronomy, that helps us in the propagation of waves in the atmosphere, that determines all these. I have a GSM. There is no link. I have a Wi-Fi. There's no link. But each of those service providers have a particular what? Frequency with which they propagate their waves. Those their waves are signals. You see? And these things are carried by waves. So each of these waves must have a boundary to which they operate. And that is actually determined by what? The cutoff frequency. It talks about the bandwidth. And then if you are propagating above, outside their limits, you start having interference. Huh? So everybody tries to control. The controllers want their signals to be within their boundary. That is what happens in radio astronomy. All right. So you see that what we are dealing with has applications, various applications in communications. All right? Okay. Now, we now want to look at what happens when we perturb this. Let's disturb it a little. I know some of you have a smaller, or your nephews and nieces, when they give them birth small, you go back home, you see they are quiet. They just play and smile small. You say, okay, let me see what will happen to this child. You do what? You slap small. The person will do, yeah, is it not? You start crying small. You have disturbed. So what is the effect of that? The first thing you will hear, if the mother is close, you say, what has happened to my son or daughter? Is it not? So we want to see what happens, because you have disturbed that child from that small, quiet environment, situation he was, to something that makes the person to cry. So let's see what that cry will be. All right? Now, as before, this is the variable. This is the steady state, and this is the perturbed state. Each of them goes for the pressure, density, velocity, and magnetic field. Okay. You can now linearize, is it not? We did it yesterday. We took almost the same time, all our time to do it. Now, we have done that. This is exactly what you will expect. You see here, because there is a gamma P naught over rho that will give us this. That is how we got this. We call it the square of the sound speed. So we are trying to remove some of the scaling. And then you have this. This one shouldn't give us problem again. If it does, we go to one river here and do baptism. Do we have river here? Unfortunately, there's no river, so we are not going to baptize anybody. Okay. Now, you see where the problem will come in now. I said, here, we have neglected the squares and products of perturbed quantities, and this is this. Next, we will reduce these equations into a single, not simple. That should be single, single equation in the perturbed velocity. So change that into, in my notes, I have it as single. Then why is he getting that? Okay, never mind. What we now do, see this, I see this equation 5.21, we will differentiate it partially with respect to t. If you look at the first term of this, if you differentiate with respect to t, what do you have? You have partial 2v1 by what? Partial t squared, is it not? Okay. You differentiate this. Will it survive? Do we have dp0? You have grad p0. You differentiate it with respect to t. It's going to give you grad of partial p0 by partial t. Will give you grad of 0, which will be what? 0. Okay? This one will survive because it's not a constant. Already we have this equation that has partial P1. So by T, is it not? Okay. Now, this will remain and that will remain. We now use 520 this and this in equation 525, you simplify, you will get this. Just like what we did the other day. That's exactly what we will get. You can see the presence of this is the only way we have t. These other ones are just simplifications from the vectors, analysis, and identities. Now, since x and y directions are not affected by the gravity depends on the z direction. They are not affected, is it not? What do? We can simply simplify the problem by adopting 2 dimensions. Now, this is where I want you to do something. We will learn how to do some things. I want you to derive that equation that we have. It is not that difficult, but it is left with us to utilize our vector technique. For example, where the problem is going to come will be somewhere here. We take V1, for example, to be equal to this, because we are trying to work in XZ plane. So you will see that. But before then, I want us to look at how you can use Cartesian coordinates to do this. Can we do that, my friends? Can we? Now see, we are having call 1 over mu 0. Can you call that in for me? I have a big bracket, is it not? I have call what? Call what? Into V1 cross what? B naught, Okay. Cross what? The brackets, this will close, this will close. Call what? B what? B naught. Aha. How do we approach this? We should know what our, say for example, call of, or you should know your V1 cross B0, because this is this one, is it not? That is what is there. So how do you do that? Having taken that V1, for example, is equal to V1x into V1y into V1z. And let us take our B naught. What is our B naught? Is 0, 0, B. Is it not? That is what we took from our inception. That B naught is that. So what do you do? What is V1 cross B naught? You have I or E, R, EY, EZ. I have avoided the use of IJ because in our problem, when we are writing E, I, so I don't want us to confuse the two I's. Okay? And at times, in Euler, we can use EJ theta. So we don't want to confuse that. Let us use the real representation of the unit vectors in the X, Y, Z axis. Now, this will give you V1, V1X, V1Y, V1Z. You have 0, 0, B0. Can't we do this? That's how we do cross product. You will see that under your EX, what will be there? We will remove this and multiply this out, is it not? What will I get? I will have B0 V1Y plus EY. I will remove this and remove this. This times this will be a minus, this times this is a 0. So I'm going to have B0 V1X. Am I correct? Yes. Now the last one, E of Z will give you 0 because this on this times 0, this times 0. So that is the first thing you will get. We have done this one. Yes? Now, because, you see, I know what you're talking. I should be minus here, is it not? Aha. You should have minus here, which means I'm going to take this times this will be plus, is it not? Minus this times this, is it not? No. This one. This and this. This and this. So there should be a minus, So correct me when I'm going, I suppose I'll put minus there. Okay. Now, the next thing is to find a curl of A, which is the same as E of X, E of Y, E of Z. Partial by partial X, partial by partial Y, partial by partial Z. Now, what is our A? Our A is this. So, which means I'm going to have B0 V1Y minus B0 V1X and 0. So we find the curl of this, which means this will be 0. This will be plus. We have to differentiate it with respect to Z. Are you following me? These are called things now. We should know this one. No. That one is when we are, no, V0 is the one that is 0. Okay, I will remove V1Y. But I just want to see the holistic so that they should appreciate it before we turn to this. I just want them to know this. Because this one now, you must understand how to operate the call. Otherwise, you cannot go into what we are doing. This also takes us to mass method in year 2. Have you forgotten? Don't forget, So, you will do this. This is 0. This will be, You are differentiating it. Then you take this one. Remove this. This will be 0. You take this. You remove this. This will come. Now, when you get that, which means we have gotten this one. Is it not? Whatever you get, you take the call again. It is when you now get this that you will take that one now and do the call of this. So you see the stages. Okay. So when you do that, then from our problem we can put V1Y to be equal to what? 0. You'll be able to get this in component form. This is the first one. This is the second one. Now, these two problems, these two equations, 27 and 28, are the result of this in the x direction and the z direction, since we are working in xz plane. Now, to further simplify the problem, we'll define this to be this. and then bring in our what? Frequency. So when you do that, next slide. Okay. No, come down. But let me just get you. Once you are walking, you should have something handy that should be helping you to see how your vectors goes. Coordinator, usually we try to get some identities of vectors. Identities of vectors, all the things we are using. So they are just here. And then these are examples from applications in Maxwell's equations. So this is comprehensive. If they can enlarge it, fine. So you should always have it.
Okay. Every student will get it.
Okay. All right, sir. So you see, once it requires us to take our time, patience. That's why they do not give mathematicians Nobel Prize winner, because they don't compete. And you know one funniest thing about mathematicians? They drink a lot. Not water. Maybe not from your own side. I have experience from my own side. Drink a lot of alcohol. And they smoke tobacco. Dangerous smoking. How many of you have known? How many of you know Professor Bala? How many of you know Professor M.Y. Bala? He was from the University of Maiduguri, came to do something at Nasarawa State. I think he's still there after retirement. In Lafia, yes. Like you are a lecturer. I was taught by a lot of, about 6 professors from Ghana. Kofinti, Achempong, and the rest of them. They're also in high energy physics, theoretical physics. They smoke a lot. The likes of Professor Baseman, they drink so much. So you understand. Don't laugh. Historians drink too. Church history drink too. Okay. All right. Now we have come this way. We have come of age. If you plug those things here, we are doing Fourier analysis, or what we call normal mode analysis. Once we put this, like here you have partial 2Vx by partial z squared. You differentiate this twice. You put here. You have Vx squared. You differentiate these two, you put here. You differentiate with respect to t, you do all this and that. Once you finish that, you will come to these equations. In the previous one we did, if you notice carefully, G wasn't here, but now G is there, is it not? So G has actually done some things. Will come. Now you can do non-dimensionalization because the scaling is too much. So we want to reduce it. We make this Z, where you see that Z, you put it as this. I will do one and I'll leave the other one for you, show you how to do it. Under the non-dimensionalization, we are, let's say you have d2 by dz squared. So, and we are asked to take z to be equal to h of z subscript h, to tell you we are working in a high scale. So, in place of this, I will have d2 by d. I will have h, I will have zh. I will square it. Is it not? Are you following me? Yes. This will give me d2 by dh squared, zh squared, which I will write as 1 over h squared of d2 by dzh all squared. So in place of our d2 by dz squared, we are going to have this. But because we also have some other things that come in here, which we will define. For example, you will see your omega squared has been defined as this, is it not? It will bring out also h squared, and so on. By the time you clean it up, you will get this. This is what we call non-dimensionalization. All right? Now, these two equations are now coupled differential equations. They are what? Coupled differential equations. If you know how to eliminate, you can eliminate Vz by operating on this one with the operator here. And that will give you a fourth order differential equations. So, our goal is to solve Vx and Vz. And once we get them, with the parameters we have, all these are new lambda days, we'll be able to do the plots. All right? You can either solve them by, if you are good, I've given you the initial conditions. They are the same initial condition when we started. You can use that boundary condition to solve this. Or you can solve it by finite difference method. Or Laplace transform. So there are a lot of methods. It all depends on you. This is a research problem. So it's not something you give to solve in the classroom. Organizer. So this is one research area that somebody can try to do, because that's our goal, to solve that. Maybe by the time I'm coming tomorrow, I may bring some certain approximations. Some people might say, okay, let us assume that this one, Kx is 0. If Kx is 0, you look for everywhere you have Kx and put what? 0. It will reduce the problem, is it not? And then further, what do we have again? Or let me go back to this one, before the non-dimensionalization. This. Let's assume that Vx does not depend on x. So this term will do what? Will vanish. Wherever you have d by dx will do what? Vanish, is it not? So if that vanishes, this first equation will be this minus this. This will vanish, this will vanish. We'll come back to our original problem where g is not there. You come back here too, this will vanish, this will vanish, this will vanish. This now is modified because of the addition of the third term here. And then if G is very large, it can also affect the problem. So if you remove this term, you also come back to the normal wave equation. So all these additions are things that evolve in the research. We want to see the inclusion of that G, what it has to do. So this is one research problem we will solve. Maybe I will start with Dr. Lewis. We will do that. We'll bring out the boundary conditions with Prof. So that's, now we will try to see consequences of including G in this system. What has G done? You can see what I discussed is what G has. Gravity will introduce directionality. The Z, are we taking Z to move upward, or are we taking it downward? These are things we'll consider. At times we can look at putting Z equal to minus Z, changes the direction, isn't it? Then you will now see gravity might now be upward, and so on. So these are things that are considered. Can you even imagine that if somebody wants to play tennis, okay, let's say you are playing a projectile, which you actually seen in golf. Most times you can see it goes up first, is it not? Before it starts traversing. Why is the essence? You are going against gravity. It's allowed. So at that level, you discover that even when the plane wants to take off, what does it do? It must go against gravity. Then stabilizes. Is it not? Yes. We know this is Z direction. which also exists in nature. Then you have gravity will now become self-gravitating, which means it's potentially dependent. I think what we'll do, they will go and look at lecture 8, which has to do with cylindrical coordinates. Let their hands strong small here.
Okay.
But I will just do this. This is just the nesting alpha wave, just the same. This is not that. So that you can now see how those things can come up. Then when we now design work to do, we can now begin to bring in other things.
Okay.
So that let us not just kill them before they die.
Yeah. Okay, this is the one you just explained.
It is part of what we'll do.
Just
This is a continuation of that two equations.
yes.
But now I have made this to be zero to
So it
reduce the
reduces,
scale.
yeah.
So you see it. So these are other aspects which at the end of the day will introduce the acoustic cutoff frequency, which we saw by Fourier like this, can reduce it. So you see, that's when we now begin to talk about that.
It's quite interesting.
Normally, if you are to be the time we go to ICTP, this is usually 4 weeks.
1 month.
Oh.
Yeah, you consider the resources.
No, I know. When you look at that,
Next year will be better. Yeah, that's why trying to see that we do more programs. Just trying to do that. And this is what the center is
it's supposed to be.
known for.
So which form are we filling?
It's the form from the Savicom.
What is Savicom?
It has to do with evaluating the services that's provided
At the center.
for this
Mm.
program. So,
Feel for me now.
no, you feel it. My secretary has gone out. When she
Okay.
comes. It's not a big deal.
There's nothing there.
It's just take.
Eh, meanwhile, they are eating all the money. How can you run a center like this, even if the NEPA is not working? They should be powering this place.
To run this one here in
Hmm.
a month, because you have a plant over there, an industrial plant. It's crazy. You can't remember when last we did that. So maintaining is really simple.
Now, you see what she was asking me. She says, see, if we're looking at acetoma medium, the equilibrium density decays exponentially fast
With height.
with height. So to reduce that, we'll replace this by S. But it still exists, But you just want to use it to get something else that will stop that from fast decay.
Okay.
And then it will modify the problem. Instead of having it as a negative, it becomes a positive, which will give you a sinusoidal. So you see, which goes on to give you bezels. So you see, these are introducing so many things.
That's another form of differential equation.
It's a differential equation. That's bezel. So if you are solving that problem with boundary condition this,
Okay.
you'll be able to get this. So
From 0 to half.
that is, this one is 0.
Yeah,
So
0 to half.
when you differentiate it,
Okay, from 0 to half. Right?
and put your s equal to this, that will vanish. Will give you these solutions.
But in real life, Prof, do these things vanish like this? In real life, or we try to make
No.
it easier?
No, when we say vanish, you must start from origin. You must start from somewhere. So here now, they say you are starting that x, because if x, for example, you see here, see. We said to replace this with this. So if you take 0 here, this will give you 1.
Yeah.
You still have this. So which returns you to the initial pressure. But if you still take that Z the way it goes, it will go very fast as it's decaying. So in less than no time, it crashes.
Okay.
So these are some of the things. Like if we go in there now, there are weak solutions. There is fast and so on. So these are things that comes in. In this one now, you will not be seeing it. But when you go to, there are weak approximations. There are things. All these are things now that makes your work different from certain things people do. That's why now the analysis comes in. You need to know, say, okay, what happened if this is not there? Because that term that has partial by partial x we are removing, what is it called? It's a kind of what do we call this? Dampness. It dampens the system. Let us remove the dampness.
Then if you remove the dampness, it will move faster.
No, if you remove the dampness, it propagates a wave properly.
Yeah, of course.
Yeah, the wave will propagate. But if the damp is there, it will give you two solutions.
Yes.
One will decay so fast, which we call transient. But what we consider will be the steady, the one that have cosine or sine, that you know that it will go, it will come down, it will go and come down. So,
That gives a more physical.
so these are some of the approximations that come in. Like I think in the.
It's like treating it as a wave. That's what happens also in the strings.
Uh-huh.
When you introduce dampness, when you introduce a resistive force. I'm talking about normal waves. Then there are waves you just allow to propagate, and there are waves you introduce damping force. And how you damping force then at the right time.
Just
The way
like,
it behaves is different.
no, they will definitely be different. Just like here now. This one does not have any dampness. But this does because of this presence. It dampens it. And that dampness comes as a result of G.
Of course.
So the velocity in the direction of x is not influenced by G. But the one that is in the z direction is influenced by G.
Of course, because it's going.
And that is what introduces dampness. So which means the speed of this will be higher than the speed of this.
Yes, this will be slowed down because of this factor.
So that is what is happening here. So it's one hour for you now to start analyzing the problems.
Are there other things that can be added? What can you see? That's another.
Well, for now, the next thing that can come in is when we look at dissipative terms. What we can call restive force can be added. Then in the energy equation, we can say, that the heat cannot be there. There must be a sink. There must be a source. So we introduce heat loss parameter. So the whole thing changes.
Because in the real situation, there will be some.
There are some. That's what we call thermal imbalance. It's also a problem. I will also give you some things I have that. Thermal imbalance. But as we are putting them, it complicates. It makes the whole thing look complex.
Yes, the more tense. Okay, you done? Hold on. This is very. Okay, look on this. You didn't use this one. Wow, great. Because you know we have this left. You got the pass from them. Okay. If I can have this identity, I want to give them now. Our own, our own. And then you can send the other ones to South. Prof has to fill this one. Prof.
For me, I'm the one teaching now, so everything will be good. I'm not supposed to feel it.
No, Prof, feel. Because you're also being taken care of in a way.
Do you people have a fire extinguisher here?
Yes, on this bed.
Well, fairly okay.
Okay, thank you, Prof. Don't worry about photocopying this, just but you can do it, be nice. You can still photocopy it and keep. If you can still photocopy that blank and keep this, then just. This one's identity. Thank you so much. This is really nice. No, that'll be later, no problem. You can give it to them by Monday next week. Did you staple these ones? You staple them? Okay, you have a stapler here. The copies for the identities have been done.
For?
The identities.
Okay.
They are available now.
Okay.
Yes. You have them.
I'll take my own now.
Sure.
Uh-huh.
Sure. Where's the original? It's already stapled, right?
Thank you. This is usually our own Bible.
Yes, it's right. Sure.
This is my own. Madam, please, can I have a bottle of water? because this is our Bible. All the identities are here and more. So normally when I get this to my students, like here you can see here, I use this a lot. So I have to do asterisk. I use this one. So surely in this course, that's only two things I've used. So anybody, you don't need to memorize them. Okay, thank you, man. It's like there's a book I didn't give you. Like I didn't give you this book.
No, you did not. You just brought this now.
No. I mean here, see what I'm saying? There's a textbook, See MAD Waves in Solar Atmosphere.
Okay.
Maybe it's not among the ones I get.
I'll be opening that today.
Okay. So, but I will send it even if it's there or not that to Solar MAD. Like your director is not coming today. Who is our class prefect? My friend, go and call your colleagues. Let's start. Because just for me, just for me to wind up.
That's what we said yesterday.
No, I mean for me to discuss on these equations, and then like these ones are on one page. Okay. How many are we waiting for? Only one or two? Just only one person. Okay. So we can continue, we can start, they will join us. Okay. Now we want to look at Alpine waves in stratified atmosphere. If you look at what we did before, can we define the Alpine wave? Now listen. The acoustic wave does not depend on the magnetic field, but the Alpine depends, is it not? Who can give us the definition of the Alpine waves? Have you forgotten? Huh? What is VA? What is our VA? What is our VA? What is our VA? It's not square root of b not squared. Over what? There's a mu 0. There is a 2. Is it not? Huh? Check the note I gave you. All of CS, acoustic speed. Is it not? Huh? Aha. So those are the two waves we have, Alpine and acoustic wave. Now I want to look at acoustic waves in stratified atmosphere. If you go previously into what we did, where we got some equations. Now, if you look at this equation, if you look at this equation that this does not exist and this does not exist, you will have this and this will be equal to 0. Now, that is what we have here, with which we have to look at the Alpine wave. Now, in isothermal atmosphere, you will see that the equilibrium density decays fast with height. Can you remember what we did in the last chapter, where we had our what did we get in chapter 5 or lecture 5, where we had that P0 is what? What is our P0? We said P0 of Z is equal to P at 0 e raised to the power of minus Z over H. And we had our rho 0 to be equal to P0 gamma over CS squared E minus Z over H. Where we introduced, here we have introduced the high scale as a result of gravity in the system, is it not? Now what we are doing now is this, as you are seeing it, because of this negative value there, you will see that if you plot it, this is your P0 of Z, and this is your Z. This is your P at 0. It will decay fast because that's an exponential function. It depends. The same thing happens with your rho. Now, we may decide to avoid such, and let's work in S, which is actually a representation. We may replace minus Z by this so that we'll be able to have something like this. Your rho 0. So if you put this in your VA, because we need to find what VA is here. Are you seeing that? VA gives you this. And then if you put B0 squared, which is also there, and this, you should be able to have this when you multiply this. All these ones are like a kind of a constant. All right. Now, we will look at our normal form. We can replace our uy by ei omega t. Once you put that in this equation, it converts it to this equation, which can easily be solved. And once you have that equation, sorry, I don't know, they might not be able to do this at this time, but you go home, look at a substitution, you have this equation to solve. Because of the presence of this, it will give us a little bit problem. So we will do a scaling by defining this, eta to be equal to this, which is this. When you differentiate that in this equation, I've done it. So if you have done your techniques of differentiation, which we normally do in partial derivatives, you will see that d by dx, you will notice that d by ds can be written as d by the eta by the original one it has there. That is z, dz. So with this, you now convert the whole problem to be in eta. And you do that substitution, you are going to have this. The problem now is we have removed z and it's now in eta. So this equation is no other thing than the Bessel's differential equation. I know the type of Bessel's you know is the one that will tell you divide by eta squared. You are going to have d2 by eta squared plus 1 over eta d by the eta will now give us 1 plus 1, all that is operating on uy equal to 0. This is a special form of, do I have, yes. So that's a special form of differential equation of order 0, which you don't need to solve. If you want to solve the problem, we use a Frobenius method of series solution. But at the level you are, you might not solve them. But if you say your thesis, you will tell us how to solve it. You can go to Abramowitz and Stegon, or any book, handbook of mathematical physics. You will get a solution. And the solution is written in terms of this, the bezels and the other bezel. Most times, we will take this because the value is very small or introduces complex numbers. So you can now see how the solution looks like. I don't know whether you have Abraham Lewis and Stegon in this your library. You should have it. I'll tell the director. There are key books they should buy you. Okay. All right. So, application. Equation 69 represents a coronal loop of length L. See, that gives you a coronal loop of length L, which is symmetric about its apex. Now, for a vanishing disturbance, because IUY now is a disturbance, if it vanishes, you should be able to have something that looks like this. And that introduces this. So you will see the oscillation that disturbs the apex can be with this boundary. If you look at that, you'll be able to have standing Alphian waves as this. So these are some applications. We can plot all of them. So that is where you now need to have some software, or you can write your own program. So you see, what we have done today, the inclusion of G in the problem has modified a lot. And that is where the basis of research should start. Let's see what happens with gravity. Does not mean that we cannot work without gravity. But once gravity is there, it becomes a little bit complicated and more practicable. The same thing we are here. Like I was telling you, that you come here, these are the equations we borrow from 528 and 527. Now, let's say that this is not there. Partial by partial x is not there in the problem. That first one will reduce to this, which you are familiar with, is it not? Now, since we have taken that partial by partial x is 0, what happens? This one will also do what? Will vanish. It will do what? Will vanish. This one will also do what? Vanish. And this equation will remain this. Now, you will see that this term is the one that is carrying G. So, if you write a second order equation that says A x double dot as a function of t, okay, let's say m, plus c x dot of t plus k of x of t equal to 0, for example. Have you seen such equation before? Huh? Okay. Now, you've seen such equation. It's a spring equation. And this spring equation has a damping force. Huh? You see that one? It's damping. If you remove it, it will give you something that looks like this when we are solving a problem. But if you remove it, you will simply have x double dot plus c plus k over m of x equal to 0, which I will write as s double dot plus omega squared of x of t equal to 0, where this becomes the natural frequency. We have, where omega squared is equal to k over m is our natural frequency. So you see, we go on and on. So you will now see that if you are interpreting the equation, you can now see that this G, this term, will introduce dampness. And then if we are looking at this as one of the problems, that we said before, or when we are talking about this corona, the heat suddenly increases. Is it not? Huh? We said that coronal temperature increases. And up till now, they've been trying to find out what causes that increase in temperature. And then we now added stratification to the problem, which is a G. So that G dampens the situation. And when it is damped, the particle cannot move fast, is it not? So which means it cannot convect its heat away. So one of the things researchers are doing in this area is what is known as coronal heating. Coronal heating can be as a result of stratification of the atmosphere. That is the inclusion of G. So you see one application. So G will slow down the motion. All right. So these two problems, 7.3 and 7.4, this is what we will sit down, or you sit down. It's one of the projects I will give you for us to do. I will give you the materials. Let's see whether we will derive that equation. But I'll just give a highlight so that when you are solving, you know what you will get. Now, these equations are decomposed into this. The equation we have for transverse motion is given in this and can be treated in the same way. Anyway, while equation 7.4 arises due to gravity effects under force-free assumption, which we started in chapter 5. Now, that equation 7.4 can be written as what we call Klein-Gordon equation. I will give you people this book, CMHD Waves in Solar Atmosphere by Bernard Roberts. So you get this equation, is what we call Klein-Gordon. This is substitution that is made. If you make this substitution in that equation 7.4, you must have equation 7.5. Q is this is normalized this frequency, and Q of A, S, is the local critical frequency, or what we call the cutoff frequency. And in that case, you see, it is modified in this form. So this is how the cutoff frequency will come under the Klein-Gordon equation. And then for isotomer, this is equal to this, and CS equal to CS. You put this, you will see that the moment you're able to follow these steps by your own time and do the differentiation, you will get this. And this is the cutoff frequency that comes in a non-magnetic, because we did what? We said that force-free removes the effect of magnetism in that area. So you will have this. There are researches. Then you have the cutoff frequency. Assume a Fourier, you will get this, which is the same way we are going to solve, where you cannot use this as your dispersion equation. If you take the square root of this, you have plus or minus square root of whatever that is there. And what is the significance of this Klein-Gordon? The presence of this. And when this is 0, this will reduce to the normal wave equation where there is no G. This tells you that the expression omega must be greater than this. For you now see, for the wave to propagate, omega must be greater than the cutoff frequency. Because if the cutoff frequency is greater than that, it's not possible for you to have a propagation. I think that's where we will end. So, any question for me? And then we should be now ready. Those who wants to work with us, we know. And now we begin to select the project area. Prof, let me so. Because this is one of the areas. You see, here there are a lot of problems here. Coordinator, there are a lot of problems here. So those who are interested should now come and follow us and take the pepper soup. Huh? But I know after yesterday's class, you followed. Huh? Did you go back to solve those problems, those equations, from one stage to the other, and so on? If you're able to get them, you are now ready with us. This now we introduce so many things, but we'll start small. Pepper soup, eh? No, the S that we added, you see, we have, if we are solving a problem, for instance, and like as I put there, assuming that we have a P cosine of omega t, for example. This is non-homogeneous, is it not? Okay. And when we solve this problem, we will get a solution of x of t, the one we call transient solution, plus steady state solution. All right? And this transient solution will be approximated by E minus a function that has to look like this of t. There might be something here, plus there's something here. This will be either cos of this plus sine of something. Okay? This is what we call the steady. This is what we call the transient. Are you following me? Now, this transient will actually give us, it's a decaying function. This is usually a decaying function, which means it dies. And if we leave that z as it is, it makes the system to die so fast. So usually we will do what? Ignore it. We usually ignore this. And then take the steady state, which is more practicable. Since we are propagating a wave in the system, we don't want the system to die suddenly. So we take this, which will propagate as you are going. It doesn't die. So such small changes brings a physical interpretation, a realistic physical interpretation. Because the kind of the space we have, we have an isotropic. We have isotropic. And in that isotopal, what happened? Remember where we introduced T. And we took that T as a constant. We didn't want it to vary. So that is why, in most cases, when T isotopal spaces are just like a quiet zone. Do you people know about cylindrical coordinates? Eh? Because that's the last chapter I wanted to do. But I said I would stop. Let us chew this one first and see how it goes. Because you still have to go and do the call of a vector. And then when you understand the call of a vector, it will be easier for us to be able to go to other coordinates. Let me staple this document that I will use with my Oga. Madam, Mommy, please, is your stapler around here? Thank you. It's like this is the only type of stapler that is working in Nigeria. That's the type I have too. Thank you. You see, Prof, you see something like this, for example. It's a problem I want to look at. These solutions of inhomogeneous magnetic slab for linear as a seismic waves. If you look at the equations, no, you can go through it after. Maybe just be going at it. I'll call it. He may make a photocopy of it so that we can. So the thing is that we look at this, we linearize it, we'll come to this. With do this treatment, we'll now be able to reduce it this far and make small approximations they have taken, and we'll now be able to see where we are going to. See, like for Affian wave, for example, you solve the problem, and then you can now begin to generate. It's a little bit, you know. So there are quite a lot of them I have. So maybe we can take our time, see what we can come out and get one or two people so that we can work as a group. Has he studied the Mathematica?
No.
Okay. Have you shared the group? Or today, after today?
We're creating it today.
So then,
Once Prof is done.
I'm done. Oh. Okay, fine.
No, once he is done.
Can you?
It's going to be a lot of work.
Have you taken a lot of pepper soup?
Ginger and pepper.
At times you can stay 6 hours, you have not left your table.
Yeah, that's how it should be. Actually.